Welcome back to Eigenlayer Unlocked with Remi from Inco. Remi, welcome on today.
Welcome to Eigenlayer Unlocked, an interactive educational journey through the Eigenlayer ecosystem created by technical founders and builders for the entire crypto community. A special thank you to our partners, AltLayer, Polymer, Authentic, Skate, and Lagrange for helping to make this happen. Our goal is to raise the collective knowledge of the Eigenlayer AVS ecosystem and unpack the technical designs of the top teams in space. Welcome to Eigenlayer Unlocked.
Welcome back to Eigenlayer Unlocked for an episode today about the idea of FHE, which is fully homomorphic encryption, with Remi from Inco. Remi, welcome on today. Looking forward to it.
Yeah, thank you for having me. Excited to talk about FHE and also broadly speaking what we're building here.
Yeah, man. Looking forward to learning how you guys utilize Eigenlayer amongst this kind of broader series and dive into some of the lower level technical architecture. So whenever you're ready, let's jump in.
Yeah, absolutely. So, from a high level, I'll introduce sort of what we're trying to, the problem we're trying to solve here, but also sort of what FHE is. And then towards the end, I can go more towards like the use cases, because ultimately, for anyone building infra, what truly matters is, what can people actually build with this, right? So what we're building is what we call the universal confidential computing network. And so the problem we're trying to solve is, today, all the layer 1, layer 2s have one thing in common. They're all transparent databases. And so we actually believe that, in order to have mass adoption, you actually need a minimum of confidentiality. So just a couple of examples. Today, when you use crypto as your bank account or for payroll, everything is transparent. And if you were to onboard a billion people to crypto systems today, it would almost be unusable because it would be social chaos. It means that your neighbor knows how much money you have. Everyone within your company knows how much you're getting paid. It's not how Web 2 works, because there are social sort of like rules that we need to feel comfortable, with this private information, and this is just not feasible today in Web3. And second, there are institutions and enterprises who have explored the idea of private blockchain in the past, Hyperledger, R3 Corda, solving this problem of like confidentiality. But these are not quite the same, because these private blockchains cannot interoperate with the other public blockchains. They also don't tap into the same amount of liquidity or user base. And lastly, just institutions and enterprises have compliance rules, trade secrets. It doesn't quite make sense for them to move to public blockchains. And then lastly, there are just a lot of use cases that wouldn't make sense without any hidden information. So think of the card games, private voting, blind auction. This idea of hidden information is just part of how you build things in general, even in Web 2. Right. So if you want to build something like eBay, you have to hide people's bids. Right. So this idea of shielded states or shielded private states is a very necessary component. So it's beyond privacy. Right. So what we're building at Inco is what we believe to be the missing layer of the blockchain stack, the confidential computing layer. So it's very similar to, if you think about the existing layers like execution, settlement, DA, we're very much, our own stack here, our own layer. And I'll explain a little bit more later on why we are our own layer here. But we utilize a cryptography called FHE. So for folks who have never heard of this term before, it's a very different type of cryptography compared to ZK. What FHE does is one thing, and one thing really well, is the ability to encrypt data, but also allow you to compute on top of it without having to decrypt. So it almost sounds like magic, right? Imagine like you have this cat picture. You can encrypt this cat picture. You're still able to manipulate every single pixel because ultimately they are RGB values, right? They're just integers. You can still add, divide, multiply on top of these individual pixels without seeing what it is. And by the time you decrypt, now you have a magical filter. So this is really what FHE really does at the core, is really just the ability for you to do compute on top of encrypted data. So not only you can do computation, operations like additions, you can also do comparisons, which are quite useful for certain applications that I can dive into later. So The idea of FHE is not new. It's been around for almost 40 years now. It actually started from the 70s. Back then, the concept was pure fantasy. It was like more around like, what if we could compute on top of encrypted data, right? It was just a wild fantasy. And so this concept of privacy homomorphism started back in the 70s. And then the first, I would say, realistic proof that this was somewhat feasible was towards the end of the 90s with partial homomorphic encryption, where you could do simple additions. And the breakthrough was done by Pascal Paulier, a legend in the space. And the next breakthrough really came much later, back in 2009, where Ted Gentry introduced this concept of bootstrapping. So I'll explain quickly like why this was so challenging. When you do FHE operations, you do them on top of something called ciphertext. So a ciphertext is the encrypted data. So you can see the picture on the left here. A ciphertext is composed of the actual data with some data padding, some noise, and noise padding. And so when you compute on top of these ciphertexts, what happens is this noise will keep on growing until it overflows, and this ciphertext is no longer valid because of it. So bootstrapping, you can think of it as a way to denoise in between operations so that you can keep this noise in check, so you can continuously do operations on top of this encrypted data without this becoming unusable. So this is the breakthrough that Craig came out back in 2009, which was a pretty big deal back in the days. But this process was still very slow. It was a very costly and slow process, so still making FHE difficult to be practical. And fast forward, another breakthrough happened back in 2021 called programmable bootstrapping. So what it is really, it's a fast stable lookup that allows you to do bootstrapping at a much faster pace in tens of milliseconds. So now suddenly FHE becomes a lot more practical because of it. One thing I like to mention is, the way to think about FHE is compute bound. So meaning that, it is quite computational intensive, but it is solvable with more hardware. So, today you can use it to compute with CPU, GPU will be faster. And there are specialized hardware that will come out very soon. There are actually dozens of companies working on this hardware for years, actually. And then a lot of them are coming out to the market next year. These are specialized ASICs. You can, similar to Bitcoin, they're basically specialized machines that are more, that can run basically specific cryptographies more efficiently. And so essentially the way to accelerate FHE is through compute. And, with the specialized hardware, things will always get, faster and cheaper over time. And so this is different, a little bit different from, some other, system that might be network dependent. For example, MPC, because for every single compute or specific operations, you need the nodes to talk to each other. Ultimately, you're sort of like, bound by the networking time, because you can go faster than the speed of light, right? So at some point with the distance, the different nodes, if you try to scale this up, especially, then it becomes more of a networking problem. But with FHE, it's really, compute bound. It's really just all about compute. So yeah, I mean, the FHE hardware research has been going around for quite some time. Even DARPA gave out some grants to Intel Duality back in 2021. There are also quite a bit of overlap between ZK and FHE hardwares as well. So it's actually quite exciting to see a lot of this hardware actually very close to being production ready. So, in the context of privacy for blockchain, this is not a new topic neither. There has been a lot of attempts solving it using more of a commitment-based approach. So you can think of maybe like a ZK-based approach. What we're using is what we call the encryption-based approach. And maybe just high-level comparison of the two approaches. What are some trade-offs? I believe that both approaches are quite valuable for different use cases. But maybe just from a high level, in terms of commitment-based approach, the compute overhead is actually on the client side. So the end user generates these ZK proofs on the client side. So it's sort of like spread out across every single user base, right? In the encryption-based approach, typically the blockchain does the state transition on behalf of every single user. So this also means the compute overhead is on the blockchain side. In terms of privacy, you could argue that the commitment approach is more private because every single user has their own encryption key. So encryption, private and public key. So basically, the secret is also stored off chain. You also encrypt using this private key, so the secret actually never leaves the clients. So in a way, it's quite private, right? Encryption, typically you depend on a third-party authority to help you decrypt that piece of information. So it could be a single key, or it could be an MPC network. But essentially, because there are risks around collusion, you can argue it's less private. But maybe privacy, the degree of privacy is also debatable, right? Depending on your use case here. But this is just kind of like from a high level. The third point here is around decryption rules. So when you have a system that's more commitment based, typically the way it works is if Andy, you transfer money to Robbie, you essentially generate a ZK proof, but also specify Robbie's viewing key. So Robbie will have a viewing key that he can utilize. He will have the private key associated with it to be able to decrypt. But you cannot have to like specify that ahead of time during the proof generation. And so this also means that later on, if Robbie loses his keys or wants to delegate viewing to a third party, it's actually very rigid. It's very difficult because sort of like the delegation of the viewing is done at the proof generation time, at the transfer time. Now in the encryption-based system, it's actually a lot more flexible because there's just a single key that everyone shares, and then you can basically change the rules so that someone else can decrypt on your behalf if you wanted to. The fourth point is around composability. So what makes FHE composable is the idea that you can store this encrypted data directly on the blockchain. And so anyone can transform it. So I can add to it, divide, multiply. So it's this idea of a shared private state where the blockchain itself is the shared layer. And so why does this matter, right? It matters because blockchains are multiplayer systems. So if you think about DeFi, right, you're always interacting with some kind of shared pool. For something like private voting, you are adding to a shared tally, right? And so having basically the encrypted blockchain states fully on chain allows anyone to interact with this in a permissionless manner and do state transition in a permissionless manner. So the blockchain itself is the coordination layer. The problem with ZK-based approaches is because all the encrypted data are stored off chain, all the circuits, the data logic is also stored off chain. You have this like prover verifier architecture where it's quite unique, I'll say, compared to your typical blockchain. Essentially, to coordinate states across multiple parties, you sort of need this centralized prover to do the tally on behalf of everyone, right? For example, for like a private voting. Now, the challenge with that is ZK cannot do state transition over encrypted data. It's not meant to do proofs over encrypted data. It has to be over plaintext. So there could be also information leakage risk because you need a centralized off-chain prover to coordinate the states and then do the state transition, right? And so,
real quick, Remi,
yeah.
just on that point, with all of those understandings with regards to the differences between like the ZK modeling of encryption and proving versus the FHE model, would you say that these technologies are complementary or competitive? I'm seeing differing opinions in like the research forums, and also people throwing in like TEs here as well as like being like somehow in the mix. Like, what is the right mental model to think about the relationship between ZK, FHE, and even like TEs as a bonus?
That's a really good question. They are essentially different tools, and they're particularly better suited for different purposes. So, for example, ZK, extremely efficient for any large amounts of computes. Imagine you were to build a game like Pokemon, right? There are hundreds of moves, and you want to choose a hidden move, right? You're better off validating the logic off-chain to make sure it's a valid move, generate ZK proof out of it, rather than doing this on-chain over FHE. So, the sweet spot from what I see is combining ZK and FHE, and also understanding, what are the trade-offs of these cryptographies. Another example is, if you wanted to break the linkage between the sender and recipients, I would say ZK is probably more efficient in that way. And obviously, it's also quite controversial, right? Return of the cache, things like that. But there are also practical reasons why sometimes you want to break the linkage. Like, I'll give you two examples. If you were to, for example, do supply chain, right? Coca-Cola does supply chain. All the vendors are typically known. So it's okay for you to pay them on chain, having traceability. You're just hiding the amount that you're paying out to the vendors. So that's okay. But for example, in the case where you want to visit a medical professional, you actually want to hide the fact that you have visited a medical professional in the first place, right? So this is where you actually do want to break the linkage between the sender and recipient. And this is where, I would say ZK-based systems actually work fine, and probably more private and more anonymous. So I guess, like, back to your point, I do think there is room for both technologies. What I'll say the encryption system does really well is this idea of composability. So any use cases that involves multiple parties, multiplayer systems, I think what ZK does really well is more around these single player use cases, more around anonymity use cases, and around, I would say, things that require a lot of compute use cases, like including like something like the ZK passport. Like if you want to prove your age, actually ZK works fine, and it's actually great.
Yeah, it makes sense. So the combination of the two is what really gets you the desired outcome for, specific use cases that want that, want that combination. You don't really see them as necessarily being directly competitive, but when put together, there's going to be interesting use cases, but ultimately, it seems like the privacy element strictly of FHE could be potentially seen as stronger in certain elements than ZK. However, ZK gives you those kind of fast finality guarantees and these things that you were speaking about previously. And so I think that, like, it's kind of a balance of trade-offs there.
So I'll go over a few examples down the line to illustrate some,
Cool.
like, the advantages that encryption-based systems have. But yeah, and just quickly on the last point on key rotation. So in the commitment-based system, everyone has this viewing key that's quite rigid. So if Robbie loses his key, it's very difficult to, you can't really rotate the keys, right? There's some challenges. You also cannot revoke access, right? Because these are predefined encrypted values under a specific viewing key. Now, in the encryption system, there are actually ways in FHE where you can also rotate the keys without just doing it over FHE directly. So I'll say key management, I'll say encryption systems are definitely a lot more flexible here. So, ultimately, there are many cryptographic solutions, but like I mentioned earlier at the beginning, what you really want is the ability for people to build things, useful things with these cryptographies, right? So the way this FHE cryptography is being implemented at the EVM level is really just in the form of new types, operations within the EVM. And so it's very typical for a Solidity developer or a new developer coming to the Web3 space to have this realization very quickly that, okay, everything I build on the blockchain is transparent. All the types are public, meaning that, yeah, I have to rethink through potential information leakage and make sure I don't store anything sensitive, or people cannot trace the execution path, right, of my logic. So what we're enabling here is the ability for people to have new encrypted types. So EUINT 8, for example, 16, 32, 128, eBool, meaning encrypted booleans, encrypted addresses. And you can also compute on top of these encrypted types. So you can add, divide, multiply. And we also have on-chain randomness. You can think of this as a way to augment the existing EVM so that you're no longer constrained to only public states. Like, what if I want to store a private information on chain, right? What if I want to store someone's credit score, someone's age, or someone's cards, right? For like a poker game. You can just use these encrypted types to encrypt values and store it on chain. But not only this, you can also compute on top of it. So you can do state transitions over encrypted data. So this is a very powerful concept because this is not just a matter of encryption, decryption. It actually means that you can build custom logic on top of encrypted data. So if you build like a private AMM, you have to be able to add, multiply, divide, right, to calculate the tokens coming out. This really opens up for, I'll say, a lot more design space around this idea of private compute. And again, this is all happening through cryptography. Basically, you don't need a specialized hardware for this. You don't have to write complex circuits, nor you don't need any off-chain coordination, because you don't have this like prover verifier system. It's all basically happening on chain. And then with FHE, you can also derive randomness. And this is actually quite useful in a sense that like this randomness is actually encrypted by default. So quite useful for example, card games. You generate hidden cards, right? So a little bit different than your typical VRF that's plain text based. That, for example, Chainlink would provide. So FHE has had 40 years of history. There are actually a lot of schemes. So there's TFHE, BIV, BGV, CKAS, and many others. I guess this is a little bit more specific, but yeah, we utilize the TFHE scheme. There are a couple benefits of this. Just broadly, TFHE does support a lot of operations. So additions, multiplications, divisions, comparisons, pretty broadly. Other schemes sometimes are constrained to only additions and multiplications, but they could be more specialized for other use cases, right? But in the context of smart contract, you want to have the ability to have a wider range of way to express yourself, right? You need to be able to do more complex operations. The other schemes, you could, some of them, you could have them do additional operations, but oftentimes they become approximations, so they're not going to be accurate. And the reason why this wouldn't quite make sense in the context of smart contract is, imagine DeFi, right? You want every single operation to be exact. You want exact computation. You can have a balance that's slightly off, or you can have a DeFi pool that has a liquidation threshold that's like slightly off, right? So exact computation is also very important. And then what I mean by non-level structure is some of these FHE schemes also, you have to predefine ahead of time how many steps operations you'll be doing. And so what happens is like you would do something like a bunch of operations and then do a big bootstrap at the end of it, versus TFHE actually does a bootstrap in between operations, so more frequently to keep the noise in check. But what you also get is this amount, basically unlimited depth of operations, right? So you don't have to necessarily know ahead of time how many operations you need to do. So also makes sense for smart contracts because, the smart contract logic can be arbitrary, right? So some dApps will have longer or shorter logic. So yeah, this is just, I guess, from a high level introduction to, there are other schemes as well. Some of them could also be more specialized for, AI, machine learning. Some of them are more suitable for smart contracts. So what we're building at Inco here is, essentially the computational compute layer for existing blockchains. And from a high level, we are a layer 1 blockchain. So back to that previous, slide that I mentioned earlier for that stack, you can almost think of us similar to Celestia in a way that like we are also a layer 1 blockchain. Obviously, Celestia is also layer 1. They provide DA as a service, but Inco provides basically confidential compute as a service. And with this, we also do store ciphertexts because they are quite big. We also do have our own consensus. So right now we're using Comet BFT, which has the property of instant finality. I can probably dive a little bit deeper why this is important. But from a high level, you actually want a system that has instant finality because any reorg is problematic in encryption systems. So imagine, I decrypt a value and now it reorgs. I cannot unsee that information, right? So there could be information leakage if there is a room for reorg. So even within the consensus, there are obviously other consensus mechanisms like Grandpa and others, right? What Comet BFT re-offers you is instant finality, which is quite convenient. The same goes for anything that's more optimistic as well, which is there is this at least 7-day window for finality, which is still risky, right? Any information you decrypt, that information is leaked, or any information you unwrap, right? So imagine a confidential balance that you unwrap, it's effectively bridging. So you do want this property of instant finality. Also, consequences could be also quite bad, basically. So I know I talked a lot about FHE this entire time, but really what we're building here is a combination of MPC, ZK, and FHE. So FHE really is really focused on compute, right? So anything related to computation, you do it over FHE. On the client side, this is where the ZK side, we utilize ZK. You generate a ZK proof for two purposes. One is you want to prove that the ciphertext is not malformed, meaning that the ciphertext is encrypted under this defined public key, and then the format, everything is correct. Else, later on this will have issues, right, on the compute side. The second thing you're proving is, as you're encrypting the plain text into the ciphertext, you also generate a ZK proof that you know what the plain text is. And this is, I'll say, important in Web3 because we're still supporting public blockchains. So it is possible for someone else to copy paste your ciphertext and then try to deploy it somewhere else and decrypt it, right? So this acts as a gating mechanism. So the only way for you to input ciphertext into the system is to prove that you also know what the plain text is. So this is what the ZK proof also includes. For decryption, we utilize MPC. So the benefit of this is that in MPC, essentially, the private key never existed. Typically, you would generate this through a distributed key generation system where every single node operator only has a fragment of it, has a key share. And so for any decryption, what happens is every single node does a partial decryption, and you need to combine a threshold of all these decryptions to recreate the plain text. So this is sort of like high level how we guarantee security across these different components, from the user side to the compute to the decryption. This is very high level here. So we'll offer the most intuitive way for people to write code. So first of all, because we're augmenting EVMs, you get to write these FHE code within the EVM, which should be pretty intuitive for developers. We'll also support the ability for FHE compute on top of existing blockchains. So this is where you could also tap into the existing user base, but also TVL. Just quickly from a high level how this works. Ciphertexts, the encrypted there, are actually quite big. So Inco will be in charge of storing the actual ciphertext. And what you're storing on Ethereum is essentially the handle. So you can think of the handle kind of like the key, right? So it's like a key value pair relationship. So you're storing essentially a representation of the ciphertext. If Bob sends money to Alice, you are adding an encrypted amount to an encrypted balance. So effectively, what you're doing on Ethereum is kind of like a symbolic execution where you're not actually doing the FHE compute. What you're computing essentially is a representation of it, right? So here we'll just hash the operation with the handle 1, handle 2. You generate the handle 3, and then Inco basically is abstracted away and will handle the rest. So now I guess onto the eigenlayer part. So we first started chatting with EigenLayer towards I believe it was October, November of 2023, and it was right after their blog post about how EigenLayer can enable layer ones, specifically Cosmos chains, to be more secure using this idea of dual staking. So I can dive a little bit deeper into the advantages that we see here. But we do have a blog post here with EigenLayer that was earlier this year that came out, really talking about these concepts. And I do think it is sort of an interesting design space. So especially for layer ones to benefit from additional security, but also I guess I can talk about a little bit more here. So basically, there are two essentially. There's when you launch a layer one, typically you have this cold start problem. And it's actually really a problem around 2 points. One is typically as a layer one blockchain, new layer 1 blockchain, your market cap is going to be smaller. So there are two consequences with that. One is because your market cap is smaller, you have higher volatility. And because you have higher volatility, typically, you have to give out higher inflation rates of your tokens to compensate for the inventory risk that all the stakers will have, right? So typical, Cosmos chains give out 20 to 50% annual inflation rate, which is, really, really high. But if you can utilize this concept of dual staking, which is, effectively staking Ethereum and Inco, then essentially you can lower the inflation rate because Ethereum market cap arguably is going to be more stable, less volatile. The second point is, because your market cap is also lower, your security is also much lower to begin with, right? So this is where, with dual staking, you could also leverage the economic security of ETH. If there are a lot of stakers, you can essentially increase your overall security through dual staking. In terms of architecture, this is definitely still, I would say, a very open-ended exploration. I personally haven't quite seen many teams being able to, completely finish this in terms of production-ready architecture, but there has definitely been a couple explorations. For example, like I can maybe share a little bit more about what we've considered. So, when you run a Cosmos chain, like we do here, what you could do effectively to get this economic security from Ethereum is to customize your L1 nodes to monitor all the states on Ethereum. And so from there, you could also inject, so you can basically observe the additional economic stake on ETH and inject that economic stake directly into your staking module on the Cosmos side. And so you could either do it, I'll say, through some kind of voting module within the Cosmos, or maybe through something like a vote extension. So I'm not sure if you have heard of vote extension, Andy and Robbie. If not, I can quickly explain that.
Yeah, I'm familiar. Please, if you don't mind.
Yeah, from a high level, vote extension is essentially the ability for every single validator to run a sidecar. And this sidecar basically can collect any arbitrary information. So I think some folks we've seen around, like, for example, Skip, what they do collect is, like, for example, the price of Bitcoin, Ethereum, and then they basically inject in Oracle pricing through the sidecar. What we could do here is, for example, monitor the voting power or the staked amount, staked ETH on Ethereum. And essentially every single validator during the consensus process can inject arbitrary data. And you can also write custom logic to basically verify that, the attested values are the same. And from there, you can change the state machine basically of Cosmos. So it's just a very convenient way to add additional external information into a blockchain system via the consensus. And so I would say that's a way that we can potentially use for this, voting power, for calculating the new voting power basically within this entire system. Yeah.
Yep, makes sense. And so this is something that this is something that Ethereum validators would run as a sidecar, and then they would also have the ability to implement this into the AVSs that they secure via restaking.
So actually, this is something that the Inco L1 validators will run.
Got it.
Yeah.
Okay.
So the Inco L1, I should have mentioned this earlier. We are built using the Cosmos SDK.
Right.
So we're using, Comet BFT for consensus. So it is very much a layer 1 blockchain. And I think a lot of people probably in the space also don't realize that many L1s that you see today, including, like, early Polygon, Binance Chain, I believe Celestia is also built using Cosmos. It's quite of a flexible and convenient stack. And, granted, we are very focused on the EVM ecosystem. To build an L1, Cosmos is still a very, very flexible tool. And so the vote extension capability is on the Cosmos side. So the Cosmos validators will run vote extension. Yeah.
Got it. Which is that, like, a lot of the purpose functionality of the Inco L1 seems to be encryption, decryption, and more cryptographic security measures. And so, how should we think about the way to balance cryptographic security handling on the L1 and then crypto economic security underneath the L1?
That's a really good question. So today, the reality is with FHE, verifiable FHE is quite inefficient. So there has been research around how do you do let's say like a snark proof of a FHE compute, right? The most costly step is around bootstrapping, and so that research basically came out with the results saying that a single bootstrap takes 20 minutes to prove today, and so we're still quite far away, I would say, to be able to do fully verifiable FHE. And so the second best option here is really via consensus. So one property that you have with FHE that's interesting is that the compute is deterministic. So this is where every single node that does the same compute can also arrive at the same conclusion, and via consensus, they can disagree or agree with each other's answers. So this is how our L1 is basically computing and also basically agreeing on the end results. Now, what's actually slashable in that context is not necessarily the compute results. I guess you could do something intersubjective here, but if you want something more objective, then probably it will happen, I'll say, later on when you can actually do some kind of ZK FHE. I'll say it will probably take some time. But in the context of Cosmos, what is slashable is the concept of double signing. So if the validators attest to different results, then you can actually cache them on that, and then on Ethereum you could actually pass in, let's say, this double signing signatures and then slash them, right? So that's doable and objective today. The FHE compute side, I would say, will probably take a little bit more time as of now. So the second best option is, I would say, consensus, and then using maybe like a more of a social way of slashing around intersubjective slashing concepts.
Yep, makes sense. Thanks.
So you get like the cryptographic guarantees of ZK, MPC, and FHE, and then you also simultaneously get this crypto economic security from Ethereum. So like, why is this not something that, or from EigenLayer, from restaked assets? Like, why isn't everybody building in this way where you get both levels of security? Like it seems like the holy grail.
So yeah, just to clarify, so today what we're utilizing is economic security with consensus. We're not doing cryptographic security because, like I said, verifiable FHE is still some time away. But it is feasible, and that's probably more of a long-term goal. What you could prove cryptographically and that's slashable is double signing. So that's outside of the cryptography. This is more of a Cosmos thing that actually does work. What's interesting is we thought about some potential interesting ways to I guess without getting too much into the weeds, some folks have also been working on this idea of like ZK how do you prove Cosmos states or verify Cosmos states on chain on Ethereum? And so there could be also slashing mechanism in that sense that we're still exploring. But yeah, definitely a super interesting area for sure.
Cool. Thanks.
So yeah, I guess onto the use cases. So what can you do with FHE and what we're building here? Essentially, you can think of an augmentation of existing EVMs, and now you can build new use cases across gaming, asset management, DeFi, and infra that wouldn't be possible otherwise, right? A couple examples. So imagine building a confidential ERC20 where Bob sends money to Alice. The balance here is confidential. So in Solidity, it's just the mapping of address to EUINT for your balance. It's an encrypted integer. And when you do a confidential transfer, essentially you are doing FHE comparison. Do you have enough balance? And then you also basically add a hidden amount to the recipient's balance, which could be 0 or the actual value here. So essentially, you are able to do conditional validation, logic validation over encrypted data, and then complete this confidential ERC transfer.
So Remi, quick question here, just like as we're putting together the pieces. It's in the long run, you'd like to do fully verifiable FHE encryption by verifying that encryption with a ZK proof. But because ZK is still kind of far off, you guys are validating or verifying the FHE computations using consensus and crypto economic security.
Yes, and a slight nuance. So we are using ZK for all the inputs, so to prove that the ciphertext is correct, but we're not using ZK for the compute because that's too inefficient. So we're using consensus for the compute today. And yeah, long term, we'd like to move towards more of a ZK based verification. Yeah.
Okay, and then from what I'm gathering, the core innovation here is that you guys have designed a way to use consensus for the computation of FHE, and the FHE is encrypted. So like the validators don't know what exactly is being computed upon this ciphertext, but they don't really need to know. They can still validate and verify the correctness of the FHE computation without actually knowing.
Exactly. It's deterministic, right? So when Bob sends money to Alice, although the values and the amounts are encrypted, the new ciphertext, right, is going to look the same across all the validators. And this is actually kind of nice because if you think about, if we were to zoom out, right, like why are the blockchains transparent, right? They're transparent because you need to be able to verify that all the transactions are done correctly, right? You need this transparency. And this is sort of like pre-FHE, right? But FHE also has this property where you can verify that all the compute has been done correctly. And now you can suddenly have encryption on top of blockchains that's also verifiable, right? So it's almost like a perfect match for blockchain technology because of this aspect that you can verify, it's deterministic. So this is what we're building. The innovation that we're building here is a blockchain layer that sits on top of existing blockchains and augments them to have the ability to have private computes. So, I like this example because it's also a stark contrast compared to something like tornado cash, right? The difference here is when I do an ERC20 transfer, confidential ERC transfer, the flow of funds is actually traceable. So if I look at Etherscan, I can see that Andy has transferred Robbie some money, but just the amount is encrypted. Versus, tornado cash, you're hiding the sender recipient, you're breaking the linkage. So here's a very different property here because everything happens on chain with FHE. You do have this traceability aspect. But like I mentioned earlier, depending on your use case, right? If you're visiting a medical facility, this is actually probably not the right tool. If you want to do some anonymous donation, you're probably better off using ZK. But if you're trying to do something like payroll or supply chain where the parties are known, you just want to hide the amounts, then this is fine. This experience is very similar to Venmo. Folks who live in the US, Venmo. With Venmo, you can see your friends sending money to each other, just not the amounts. For folks in Europe, it would be something like Revolut, right? So we're effectively able to replicate that experience, I'll say, in Web3, and that's sort of been a missing experience. And like I said, like a lot of these things, it's not even really about, it's just the practicality of at least having some confidentiality. Because the reality is, if I transfer you money, even $5 on chain, immediately you know my net worth, all the things I've bought in the past, all the people I interacted with, right? It's quite also dangerous. Like, what if a bad actor, gets to know you, right? Your neighbor, for example, could be a bad actor, right? Then you're also putting yourself at risk. So moving 1 billion people on chain, in my opinion, today is would actually create a lot of social chaos. It's very difficult to make this practical. I would say like what we're building here, if you think about like the early internet, nothing was encrypted. You had this, HTTP essentially. So you can only do academic research, things of that nature. You really needed HTTPS, so SSL, TLS, to start encrypting credit cards, payments, and bring in businesses to the internet, right? And so in a way, like we see Inco as this infra that essentially enables encryption to blockchains, but here it goes beyond payment, right? Because it's reintroducing this concept of private states to the blockchain world, basically. So like I guess like beyond payment, right? Like even poker, it's crazy to think that we still don't have fully on-chain poker games in crypto. And the reason why is you just can't hide data. It's a bluffing game. This game would just not make sense without the ability to hide data. And so this is where we are able to generate a hidden integer that are quite useful for games and such. We built this fun game about a year ago during ETH Global. It's a fully on-chain mafia game, so also known as Werewolf. Basically, 4 or 5 players will play together, and there will be a doctor, police, a secret killer, and some villagers, right? And so this game is easily done using our tech because everything happens on chain. It's a multiplayer game. It's a multiplayer system. It's very, very difficult to build the same game using ZK because everything will happen off chain and you need to do coordination. We talked to various teams who have tried to build this using ZK, and they just end up not being able to finish the game, or just end up wasting a lot of time just working around the challenges and complexities. This game was done within 24 hours because everything happens on chain. It's a coordination game, multiplayer game. It's just a lot easier, basically. One benefit that's interesting with, I'll say, encrypted compute is you have MEV protection by default, right? Because if you're hiding the amount you want to swap out, for example, you're sort of masking your intent. So bots can really sandwich attack you, right? Or they could take a risk, try to sandwich attack you, but just an interesting property here. And then for something like private voting, again, it is a multiplayer kind of like use case. So having this shared layer where everyone can cast their votes is quite convenient. And so I would say one thing that people need to understand when building using FHE is to how to design around conditional. So there's no if-else statements in FHE, because if-else statements that you have in regular code does leak information about the underlying value, right? So depending on the branch that you execute, you actually reveal what the underlying information is. So there is a clever way to do this over FHE using a multiplexer. So quickly, I can walk over a example. So imagine we're building private voting. The encrypted choice can be 0 or 1. And so the first thing you do is you can compare if this encrypted value if the encrypted choice is equal to 1. And what you get is an encrypted Boolean. And so what this really means is when you pass in this encrypted Boolean into this CMUX, which is a conditional multiplexer function, it will return the encrypted vote counts if the encrypted value is true, but 0 if it's false. So it is a conditional over encrypted data, kind of like a ternary in JavaScript. And then you do the same thing for against, where you return 0 if the encrypted value was true, and then the vote count if it's false. So one of these values would actually be the encrypted vote count. The other one would be 0, right? You're just doing the reverse. And so you add both of these encrypted values to their respective tallies. And so again, from the outset perspective, because everything is encrypted, you can't really tell, if the user voted for in favor or against, because you just end up doing tallies over encrypted data, basically. I would say that's probably the slight nuance that most people have to learn when building using FHE here. Yep. So we are compatible with existing Ethereum tooling. We've hosted quite a bit of hackathons already, and one of the bigger feedback or positive feedback is that people can start building very quickly. And we are supporting a pretty wide array of operations and comparisons. So it's really I would say a greenfield opportunity for people to build novel use cases that wouldn't be possible otherwise. And yeah, it's really just about identifying new problems to solve, unleashing your creativity. And at Inco, we are very passionate and excited about novel use cases. So definitely come talk to us if you have any ideas. We're happy to help you refine your ideas, provide feedback. And yep, some of our docs, you can check out our docs. We are making some significant updates pretty soon, so the docs might change. There are some mini games that you can play around with arcade.inco.org. Definitely reach us out at on Telegram, but also email, and we're pretty active on Discord as well. So definitely don't be shy and come talk to us. And yeah, this sort of concludes the overall introduction here.
Awesome. Yeah, Remi, I mean, really great conversation and presentation today. I think this is the first of its kind on the roll up. So excited to get this out, and thank you for joining today. It's been great.
Yeah, absolutely. And yeah, thank you for having me.
Cheers, man.